Start by yeah. Okay, so I thought so let's cap a couple of things and then I will okay, where's my one note? Okay, let me do a quick recap. So yesterday, what I did was to define Markov chains. So Markov chain is defined by two things: a state space, which is a finite or countable set, and a transition probability, which says that if you are at state I, then you move to one of the other states, and the probability that you move to state j is Pij. So this is how one step of a Markov chain takes place. So you just choose wherever you are, depending on that, you choose according to the probabilities Pij. And then you move, and we saw many examples. And I also stated some questions. But maybe first I will show you a couple of simulations. Okay, well, what happened here? Shit. Uh, So I shared some notes yesterday where I start in those notes I start with some motivation, the original motivation of Markov in model in defining in introducing Markov chains. That motivation has something to do with modeling text. So when you look at text, like you take a novel and then you look at the text, one can think of the letters or the characters that appear as some randomly chosen from the alphabet. But if you try to model them as independent random alphabets, they don't seem to fit the data well. And Markov did something, they introduced Markov chains to get a better model. That's a rough story, but I don't want to go into that. Instead, what I want to is just show you a few simulations just to say I mean, to make these things a bit concrete. All of this can be, you can put it on a computer and see it, and that makes it much more clear. So in the interest of time, I already prepared a couple of simulations. So is everyone able to see this? This is visible, right? What I'm showing here?
Yes, it is.
The Mathematica. Okay. So this is I'm doing this on Mathematica. So what I'm doing here is showing you a simulation of random walk on this graph. There is a graph with 5 vertices labeled 1, 2, 3, 4, and 5. And what is random walk? What is the station? What does the transition matrix for this random walk, simple random walk on this look like? Remember, simple random walk on that graph means if you are at state 1, you go to 2 or 3 with probability half. That is shown by the first row of the matrix here. This is the matrix P, which is the transition matrix. If you are at first row, it says that you can't go to 1, but you can go to 2 or 3 with probability half each. You can't go to 4 or 5 in one step. And if you are at state 2, then you can go to any of 1, 3, 4, or 5 with equal probability. From 2, you cannot go to 2, but all the others with equal probability. And if you are at 4, you can only go to 2. So fourth row, if you see, from 4, you can only go to 2. From 3, you have 3 places to go, and so on. From 5, you have 2 places to go, and so on. So this is the transition matrix of the Markov chain. Okay, just to show what it is like. Now we can actually run this Markov chain and see what it looks like. So here I have just, I'll run it for 1,000 steps, let us say. What I do is I pick some random numbers and according to using the random, actually this is irrelevant. So let me delete this. This is directly, so I start at the state 1. X is to start with 1. And for 1,000 steps, what I do is at each point I add one element to this append, forget that. The main point is this random choice. What I do is, if currently I am at state x of k, when at k, x of k is where I am, the Markov chain is right now, then you pick randomly among the the adjacency list tells you all the neighbors of that point, and you pick one at random, and then you run it. So here is, I just run, okay, sorry. So I just, first I have to run this one. This is the graph. And then suppose we run it for 1,000 steps. Okay, what is happening? Okay, it ran. So you see, this is the trajectory that we got. I have only shown you the first 20 steps. So from 1, it goes to 3, then it goes back to 1, it goes back to 3, it goes back to 1, it goes back to 3. Several times it happens. Then from 3 it goes to 5, goes to 2, goes to 3, and then goes to 5, 2, 1, 2. I mean, in this, so far it has not yet gone to 4. I mean, somehow. Okay, but if you draw it for much longer, it will sometime visit 4. And after 1000 steps, this shows you how many times it visited each of the vertices. This is a very easy one. Just do a tally. It will give you the how many times it visited all the vertices in the first 1000 steps. It shows that it visited the vertex 1 166 times, vertex 2 326 times, vertex 3 was visited 248 times, and 4 was visited 75 times, and 5 was visited 186 times. This was a question I asked yesterday with a different one, but the idea was which one do you think it will visit more? The idea is that higher degree vertices should be visited more and lower degree vertices should be visited less. In fact, if you see, 4 is a degree 1 vertex. It was visited 75 times. And 1 and 5 are degree 2 vertices. They were visited 166 and 186 times. Okay. So double of 75 would be 150. This is supposed to be like double of that. Whereas degree vertex 3 has degree 3 and it is visited 3 times. 70 into 3 is 75 into 3 is something like 235 or something. Sorry, 225. So that is approximate, that is how many times it visited. And 4 times 75 is about 300, and that is how many times 2 was visited. Okay, so if you can do it for much longer time, you can run another trial. Let's now run it for 10,000 times and see what happens. So now there is a different trajectory here, and you see this is like that. 820 times, 9 times it visited vertex 4. About double that time it visited 1 and 5, 1600. About 3 times that it visited vertex 2, and 4 times that it. So not only is it more, this simulation is telling us something that we should try to prove, that the number of times it visits a vertex is proportional to the degree, probably. Okay, so this is one of the key questions that we were asking about the long-term behavior of the Markov chain. Okay, any questions about this simulation? This is to illustrate random walk on a graph. I took a very simple graph, that's all. Okay. If there are no questions, let me show another one, the Ehrenfest chain. Okay. So here, what I have taken, I have already simulated this. N is 10. Okay. So, well, strictly speaking, this corresponds to 9 because in my case, Ehrenfest chain goes from 0 to n. Here it goes from 1 to 10. So this is there are two Markov chains. So this is the graph. From any vertex, you can go from 1, you can only go to 2. From 10, you can go only to 9. But from 7, you can go to 6 or 8, both of them. But there are two different Markov chains with the same state space I am running here simultaneously, just to show you how different they are. One X is the random walk on this graph. That means if you are at any interior vertices, it will move to one of the neighbors with equal probability, half and half. If you are at 1, you will go to 2. If you are at 10, you will go to 9. That is simple random walk on this graph. That is X. Y, on the other hand, is the Ehrenfest chain. What the Ehrenfest chain does is that, if you remember, if you are at vertex 4, it will go to 5 or 3, but not with equal probability. It will go to 3 with probability 4 by 10 and 5 with probability 6 by 10. Okay, if you are at 1, it will go to 2 with full probability, 10 by 10. Okay, yeah. So you may remember the Ehrenfest chain. So anyway, I run both of these, and after I have plotted after 10,000 steps how much time they spent in each of them. Instead of writing the tally, now I have dropped a histogram. So you see the random walk, it seems to spend roughly equal time in 2 to 9 and a bit less in 0 and 10, as we should expect because these have degree 1, everything else has degree 2. You see, it spends about double the time in all the other vertices and half the time in 1 and 10. That makes sense. But look at how different the Ehrenfest chain is. It is not spending much time at the ends at all. It is spending most of its time in the middle. This is in fact, looks like the binomial distribution, and we shall see, in fact, this is the binomial. It spends most of its time in the middle. This is the behavior of the Herrenfest chain. So this is two different chains in the same state space showing completely different behavior. Okay. Any questions about simulation? If not, then I will move to back to the lecture. But if there are any simulations, then I can show on the screen, because now I'll share the other one. Okay. Okay. So I come back to my notes, and so I put down 3 questions of interest. So these are the 3 questions of interest. So if you have a Markov chain, what is the after a long time t? Suppose it starts as same. So I'll just recap the questions, and then I will go on to answer these questions one after another. Maybe not all of them today, but we will answer all of them actually. So first question is most important question of Markov chains, very important one. If you start the Markov chain at state I, after a long time, what is the probability it is in various different states? Probability that xt equal to j, given that you started at state I at time 0, what is this probability? Like, does it have a limit as t goes to infinity? And does it even depend on where you started? Does it remember or does it forget where it started? So this is the most important question of long-term behavior of a Markov chain. Okay. So then there is another interesting question, which is of Polya's question of recurrence and transience, which is a beautiful question. Okay, so it's not okay. To me, question 1 is more important than question 2, but it's a very fascinating question, which is that you take a graph, usually an infinite graph, and you start the random walk on that graph, and the question is, does it visit every vertex, and does it do so infinitely often? How do we tell this? So the third question, and what I mentioned to you last time, is that if you take the graph to be z or z2, the answer is yes, it will visit every vertex infinitely many times. Whereas if you go to z3, the answer is no, it doesn't visit vertices. In fact, it doesn't visit any vertex infinitely many times. Okay, and it misses many vertices. So that is the interesting behavior of the Markov chain. The third question I asked is of gambler's ruin type, which is you have a Markov chain here pictorially depicted like this. This is the full state space. We have fixed 2 targets, A and B. Let's say A is good for you, B is bad for you. And when you run the Markov chain, we see which one we hit first, whether we hit A or whether we hit B. Okay. And what are the probabilities? Depending on the starting state, what is the probability to hit the set A before I hit the set B. Okay. So these are 3 questions. So the nature of the question is like this. You see, everything about the Markov chain is in the transition matrix. The state space and the transition matrix, there is nothing more to a Markov chain. And this transition matrix tells you in one step what are the probabilities to move to, if you are at one state I, what is the probability to move to state J in one step? That is what the transition matrix tells you. One second, what is this? Hold on. Oh, yeah, so that is the one step thing. That is a bit like, but these questions are not about one step. Question is about long-term behaviors of the Markov chain, or something that the Markov chain does over a long time. Now, that is very much like in the spirit of, I mentioned last time, Newton's laws and so on. If you remember basic mechanics, how does it go? Basic laws of physics are given by some differential equation. Like Newton's law tells you the acceleration is proportional to, the force and so on, right? So it tells you the differential equation for second order derivative for the position. Now, from that and knowing the initial position and velocity, if I ask you after a long time, where will it be? For example, think of all the planets in the solar system, all the satellites. Suppose I tell you all their positions and velocities today, and I ask you what it will be 1 year later or 1 century later, you can work it out. In principle, you can work it out from Newton's laws. The differential equation, you have to integrate the differential equation to get the answer. So this question is very similar nature. Here time is discrete, but what the Markov chain specification tells us is what happens in one step. Okay, what are the probabilities to move in one step? And the questions are what happens over a long period of time. How do we figure that out? That is the main question. Okay, so this is what we would like to answer. Yeah, so all these questions can be answered in some special cases easily, but maybe, yeah, so let's take, for example, yeah, so maybe I go one by one to keep it a bit streamlined. Let me go to question 1 and let's study that. Okay, so let me. So, question 1, long term behavior of a Markov chain. So, the question here is, so we have a Markov chain. So let me just write down the question again. X0, X1, X2, dot, 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 Markov chain, state space S, and transition matrix P. Okay. And we will take in this, for this purpose, we will take to be a finite set. For this question, I will not worry about the infinite situation, which can also be studied and is of interest, but a lot of Markov chains have finite state space. I am going to assume for now that the Markov chain is has a finite state space. Okay. So this will be true till I finish question 1. The question was, limiting behavior of probability that xt is at state j if the Markov chain starts at state I. You can think of the, always it's good to have some examples in mind, like the random walk on a finite graph. You have some finite graph. So let me just write down some finite graph here. Uh, okay. So in this finite graph, you can run the Markov chain starting at, let's say, state 1 and run it for a long time. What's the probability it will be at state 2 after 1 million steps? That sort of question is what we want to understand. Okay. So let's do a very simple situation. Okay. Let's do a very simple situation to see what happens. Okay. So let me take one example rather than jump to the question directly. So an example. Two-state Markov chain, where S has two states, which we can call 0 and 1, and P is, with probability 1 minus alpha it stays, with probability alpha it moves, with probability 1 minus beta it stays at state 1, and with probability beta it moves from state 1 to state 0. Okay? So this is where alpha and beta are between 0 and 1. Okay? So, okay, actually, sorry, I jumped a bit too much. So let us actually do it. So I'll come to this example. Before that, I want to do something else. I mean, I want to say something in general and then come to this example. Apologies for that. So The point is the answer should be there in terms of the original, because the original stationary transition matrix has everything about the Markov chain. So the question is to determine all this in terms of P. Okay. So the idea is, so far when we wrote P as a matrix, so this is one thing I should point out, that here we said P is a matrix. But okay, what is really a matrix? So here it is just a table of numbers. Okay, it's just a table of numbers that we wrote like this. It's a, like here, it's a table of numbers. It's not, is it really a matrix? Yeah, you can call it a matrix if you like, but it doesn't, unlike in what we do in linear algebra class or something, this is not coming from some linear transformation or anything. It's just a convenient way to write a table of numbers. Every table of numbers is not strictly speaking a matrix. For example, what does it mean to do matrix operations make sense here? But what we will see now is that, in fact, it is correct to have called it matrix. It is seriously a matrix in a useful sense. Okay, so what I mean by that is, so let us do it. So let's, okay, what happened here? Yeah, so let's do it for slowly for t equal to 1. Okay, what is the probability? We are interested in this. Before going to the limit, let's see if we can calculate that. Probability x1 equal to j given x0 equal to I. What is that probability? Okay, in terms of the transition matrix, can we tell what is the probability that you will be at state j if you start at state I at time 0? After at time 1, you have to be at j. What is this probability? Anyone? So if I start in this random walk in this graph, if I start at state 3, what at time 0, at time 1, what's the probability I am at state 2, for example, in one step? What is that probability?
1 by
I
3.
guess entry of
1/3.
that matrix.
In this case, it's exactly 1 by 3. In general, what is it? It is given by,
Yeah, 1 by the degree.
that is for graphs. In general, the Markov chain, that's what this P matrix tells us. By definition, this is,
I guess entry of P.
right? This is Pij, right? P, this matrix P, this is what it tells you. That's what the matrix is telling you. If you go back to the definition of a Markov chain, you can tell everything about a Markov chain up to this time. Okay, if you tell you why you are at time 0, time 1, time 2, up to time t, the probability in the next step you will be in j is from the last step, wherever you are now, I to j, Pij, that is the probability to go to the next step. Okay, so in general, that is Pij. So in particular, for time 0 to time 1, the probability to go from I to j is Pij. Okay, that is given by definition of the Markov chain. By definition of Markov chain or transition matrix, that is what it is. Now let's do t equal to 2. Okay, when I do t equal to 2, what happens? What I want is probability that at time 2 I am at state j, given that at time 0 I am at state I. So let's again take this case. Suppose I am at x0 is 3 in this case, and I want x2 to be, let's say, 2. So what are the ways in which I can go from 3 to 2 in 2 steps? I have to go there in 2 steps. So I can go from 3 to 1. So there are 2 possibilities. I go from 3 to 1 and then 1 to 2, or I go from 3 to 4 and 4 to 2. Right? So what is the probabilities of these things? So the probability here is 1/3. 3 to 1, the probability is 1/3. And 1 to 2, when you're at 1, you can go to 2 or 3 with equal probability. So this has probability 1/2. What about the other way? It's also the same. 3 to 4 has probability 1/3 and 4 to 2 has probability 1/2. So what's the probability of this trajectory? So the total probability is 1 by 3 into half for the top trajectory plus another 1 by 3 into half for the bottom trajectory. So this is going to be the probability to go from 3 to 2 in 2 steps, exactly 2 steps. So how should I do that in general? Well, what we should do is sum over all the possible. Just like here, what I did was, I don't know what happens in 2 steps. What I know, what P tells me is what happens in 1 step. So we should sum over all the possible intermediate trajectories. Okay, so let's do probability that x2 equal to j and maybe x1 equal to some k given x0 equal to I, and I sum this over all possible intermediate states. If at time 0 I am at I and time 2 I have to be at j, at time 1 I have to be at some k, I don't know which k, any k, so I sum over all the possibilities of k, right? Now what is the probability given here? So this probability is, just to write it out very in detail, so I have to go from I to k in 1 step. From time 0 to time 1, I have to go from I to k. And from time 1 to time 2, I have to go from k to j. So what will be that probability? If let me write one more step. So you can write like this: x2 equal to j given x1 equal to k, x0 equal to I times probability x1 equal to k given x0 equal to I. Okay, so if you don't understand that intermediate, you will directly understand this one. So if that intermediate notation confuses you, ignore that. What I mean is that this probability to go from I to k and then k to j, the probability is, first I have to have pik, and then from k to j I have to go. So that probability is, you are at state k, you have to go to state j, pkj. So this is what is the probability to go from from I to j in 2 steps. Okay. If there are any questions at any time, do interrupt me, like I said last time. So, okay. So this is the probability to go from I to k from time 0 to time 1. This is the probability to go from state k to state j in time 1 to time 2. So when I sum over all the intermediate positions, x1 I don't care what it is, I sum over all possibilities of x1, I get this probability. Okay. Now, can you recognize this? What is this pik, pkj summed over k? Okay. So let's write p is, so the ith row will have pi1. Let's say the state space is 1 to n. So pi1, pi2, pin. That is the ith row. Okay, so let's take S to be, take S to be 1 to n, then the ith row will be this. But let me write another copy of P here and write the jth column. Write the jth column. What do I have in the jth column? P1j, P2j up to Pn comma j. Okay, and what am I doing here? This is, if I write it out, so when I multiply these two matrices, okay, if I multiply P by P square, I comma j entry will be what? I take the ith row, multiply the jth column. So it will give me pi1 p1j plus pi2 p2j plus dot 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 pin pnj. And that is exactly the same expression that I have here. If you notice, that's what I mean by this. Sum over k is exactly, I'm summing over all the intermediate pik, pkj summed over k. That's exactly what is happening here. Is this okay? So what is this then? This is just nothing but if you take P square, the product of the matrix P with itself, and take the I comma j entry, then that's what gives you the two-step transition probabilities. Okay, two-step transition probabilities are like this. That is, now you see what I mean by, I meant that this is really a matrix. We are multiplying it like we multiply matrices. Okay, the matrix multiplication has a very specific form. It's not multiplying the ij entry by the ij entry. We take the ith row and multiply by the jth column in this fashion, right? It's a very odd definition of multiplication, but we see that is what shows up here. And so it is correct to take this P as a really a matrix seriously. So the product of the matrix is coming up. So any questions here? So what I am saying is that the second transition in two steps is given by the entries of P square. What happens when I take time 3? So I am interested in what happens. What's the probability? X3 is J, given that at time 0 I was at I. Okay, so let's do that one. So what should happen? So I have to start at time 0 at I, and at time 3 I have to be at J. So at time 1 and time 2 it can be anywhere. I don't care, right? So what all are the possibilities? So from I it can go to some K, and from there it can go to some L and then come to J. I don't care which K and L. So I should allow all possible K and L. So I only care that it should start at time 0 at I, and at time 3 it should be at J. That means at time 1 and at time 2 it should be at some K and L, which I don't know what they are, but I take all possible K and L and I sum over all the possibilities. So in other words, so what should be this probability? So let's just write it directly without and if that is not clear, I will explain further. What I am saying is that all possible. So if from I to K, K to L, L to J, that probability is Pik. So one step transition is probability is Pik. Then from K to L, the probability is Pkl. And then from L to J, the probability is PL comma J. But K and L, I can take them to be anything in the state space. I don't care which way it gets to J in two steps, it can go in any trajectory. So all these trajectories are possible ways to get from I to J in 3 steps, and we sum this over. And what is this number? Pik, Pkl, Plj. When I sum over K and L, what do I get? What is this number? Anybody? In terms of the matrix P, can I say what this quantity is? Okay, if it's not clear, so let's do just sum over K. First sum over K, I get Pik, Pkl, and then Plj comes out, right? And then I sum over L, suppose. Okay. Now, what is the inner sum? Pik, Pkl sum, what is that? Sum over K. Yes, anyone?
Piij ILth element of P square.
This is IL element of P square, right? PIK, PKL. So this is P square matrix. We have to look at the I comma L entry because that is what I have here, PKL. And then I have P, L, J, and now we are summing over L. Again, we are taking two matrices. One is P square, IL entry, and then PLJ entry. So what will this do? This is like multiplying P square with P. Multiply the two matrices and take the I comma J entry. What do we get? Ith row of P square will have P square I comma L, and then jth column of P will have PLJ, and we sum that over. So which is P cube I comma J. Is that okay? So what I am saying is that this entry is nothing but P cube I comma J. Okay. Should I explain or is it clear? Or anybody, if it's not clear, I can explain these points more. What I am saying is that this multi-step transition probabilities, if we take P and multiply, we can get those probabilities. So more generally, if I want probability that I start at state I at time 0 and at time t I want to be at state j, then I take the matrix P. T is, remember, T is a natural number for me, although T always looks like T is for time, and for us time is discrete. Okay, natural numbers which include 0 for me. So P raised to the power T. So you multiply the matrix P with itself T times and then take the I comma J entry. That gives you these probabilities. So this is the matrix power. To Tth power. Okay, to the Tth power, that is what P power T is, and then we take the I comma J entry of it. So how do we prove it? I mean, so you can write it out like that. One way to prove it, maybe I will leave it for you. So exercise, prove it by induction. So if you want to go in, let me give a hint. So if you want to go at time t equal to at time 0, you are at I, and at time, let's say, t plus 1, you want to be at j. So you see at time t, you can be at any k. Okay. Now what's the probability to go from I to k in t steps? That is p power t I comma k inductively. And then, so this will be p power t I comma k, and then to go from k to j in one step will be p k j. So when you multiply and add up over k, it is p to the t I k. So you will get sum over k, p to the power t I comma k, and then p k comma j, which is just p to the t times p I comma j, which is p to the t plus 1 ij entry. So that's how you prove this. Okay, so I will leave for you to complete the proof to your satisfaction. But if you did not follow this, what I was saying here, still just take this for granted, because this is the key thing which now is absolutely the key point of this whole. And the reason why I'm doing, there are different ways to study Markov chains. The way I am going to do will use matrices, and because this course says graphs, matrices, and applications, so I want to use matrices and our knowledge of matrices to do this. Okay, so if you have any questions, I'll answer, but even if you did not follow, take this result for granted. So what P tells you is one step probability. If you are at state I now, next step, the probability to be at j is Pij. But if you are at state I now and after t steps you want to be at j, the probability is given by the matrix power of p to the tth power and then take I comma j entry. That's what the result is. So this result is very important. And what this does is, for example, for my question, whether this limit exists, probability xt equal to j given x not equal to I, now I see that that quantity is just the tth power of the matrix P and take the ijth entry. So the question becomes, is reduced to a matrix question. It was a probability question here. What are the probabilities to be in different states after a long time? Now it's just a matrix question. I just take P to a large power and what are going to be the entries of the matrix P. Okay. Any questions here? I'll pause here and then because I want to show, but if there are any questions, I can answer now.
Sir, if we take a T to be arbitrarily large, so it is practical possible to calculate this.
That is really the very, very good question. That is, although it looks like we have solved the question, well, how do I raise a matrix to a very large power? This is the big problem, right? I mean, so we have not yet solved the problem. We have just reduced the problem from probability to matrix or linear algebra question. Okay. So let me just go back to my simulation and show you in that example. Let us take, for example, let's go back to this random graph, not random graph. So there is a graph, right? 1, 2, 3, 4, 5. Okay, for that, this is the matrix P. This is the transition matrix P. Is it okay? So I have the matrix P, which is this P, capital P. So let's see what happens. So in Mathematica, if I want matrix P to power, okay, for a moment, let's just take the power 2. Let me just show you, just to show what I said. So when I raise P square is matrix power of P2 means P dot P raised to the power 2. So it has these entries. Okay, so just let me explain one of them. It's exactly what I was doing here. In 2 steps, what's the chance to be, if you start at 1, what's the chance to be at 1 after 2 steps? Well, you can go from 1 to 2 and come back, or you can go from 1 to 3 and come back. Okay, so 1 to 2 and come back, that probability is half into 1/4. That is 1/8. And to go to 3 and come back is half into 1/3. So it is half into 1/3. That is 1/6 plus 1/8. I think that is what this 7/24 is. So like that, we can get these numbers. Okay, this is doing it on a computer. Doing it directly would be painful. Now, if you do it for 3 steps, so you see, even in 2 steps, there was no chance to go to from 2 to this is the state 4. From 2 to 4, why can't I go in 2 steps? No, I can go in 1 step. I cannot go from 2 to 4 in 2 steps. That's why I have a 0 here. Okay. So suppose you raise it to the power 3, you will get what happens after 3 steps. Okay. After 3 steps, it will tell you, okay, these are the probabilities to be from 1. If I want to know, if I start at state 1, what will be the probability to be at 4 after 3 steps? That is given by 1,4 entry of P cube, which is 1/24. Okay. But what we are interested in is as limit as t goes to infinity. So this, let me just take numerical. N of P means it will do it numerically. So let's raise it to a very large power. How large? Let's maybe make it 25. So let's say we raise it to the power 25. What do you see? So when we raise it to the power 25, you see that almost all the rows are actually the same. Right? I mean, if you just round it off to first 3 decimal places, they seem to be the same, almost. 0.166 here, 0.333 here, 0.250. So what is this telling us? That what is the first row telling us? Okay, first row is for starting at state 1. If I start at state 1, after 25 steps, the probability that I will be at state 1, 2, 3, 4, or 5, those probabilities are given by these 5 numbers. And you see the least probability is for 4, which is 0.08, and approximately double that probability seems to be at 1 and 5, 0.166 and 0.166. Approximately 3 times this much is at 3, and 4 times that much is here. Another interesting feature is that all the rows are approximately same, which means that it doesn't matter where I start. Instead of starting at 1, if I started at 5 or 4, still the probabilities are approximately in this numerical example. Is this okay? So this is to illustrate that sometimes it seems that the answer is rather clean, that when you raise this matrix, transition matrix, to a large power, you get some things, all the rows will be same, which means that the initial state is being forgotten, and there are these numbers. So this is exactly saying that the answer to my question is yes in many situations, or maybe there are exceptions we have to figure out. And now the question is, how do we prove it? Now, we can't do like this. This is a computer for a specific matrix. It was calculating the power. But in general, we will not be able to raise it to a power. So how do we do that? That is the big question. Okay. If there are any questions on simulations, I'll take. Otherwise, I'll go back to the... So you see, the difference between this and what I did earlier is what I did here this was simulation by probability. I actually ran a Markov chain. I counted how many times it visited various states. Now, because of my calculation, I know I don't need to do that. I can only calculate the matrix P to a large power and see the numbers. And that will tell me the probabilities. But still, we don't know how to do it without a computer. So that is what we need to figure out. Okay. So let me write the upshot of all this. So probability that xt equal to j given x naught equal to I is the matrix P raised to a power t and I comma j entry. So the question is how to raise P to a large power. And find the entries. Okay, and also I want to take limit t going to infinity. Okay, so large power means I'm interested in t going to infinity. What happens to these things? Okay, so how do I raise a matrix to a large power? This is actually whether or not it was put like that in your linear algebra class. Actually, one of the very important things you did actually enables us to do this problem. Now we come to an actual interesting situation where we can how some tools of linear algebra will help this. Okay, so generally speaking, raising a matrix to a large power is a really hopeless task. We will not be able to do that. Multiplying matrices is a pain, and if you have a numerical example, you can put it on a computer, but otherwise we are stuck. Okay, so but here is a suppose, so there are things you have done in linear algebra. Can you tell me anything that could help in this situation? I mean, if anybody has a guess. Is there any matrix for which you can raise to a large power? Are there some special matrices which you know how to, which would be easy? to raise to any power?
Diagonalizable matrix.
Diagonal matrices. So if you have a diagonal matrix, you can raise it to a large power. It is just that all the diagonal entries get raised to that power, right? So that's a great one, because why? Let's just suppose. So I'll now say a few things with a suppose, and then we will ask whether we can actually suppose. Suppose P is diagonalizable. That is, P is of the form x d x inverse, where D is a diagonal matrix. Okay, so this is an n cross n matrix. Let's say n is the size of the state space. So then P is an n cross n matrix. So X is some invertible matrix. So here P is n cross n, X is n cross n, and D is also n cross n. This is some invertible matrix, and D is of the form, it looks like D1, D2, Dn. And all the other entries will be 0, right? What will be in D actually? How do these entries, what do they have to do with the matrix P? They are actually the eigenvalues of P, right? So you know that under conjugation, eigenvalues don't change. So if at all this is possible to diagonalize a matrix, that diagonal matrix must have the eigenvalues of P. Okay. So anyway, we'll come to eigenvalues. These will be actually eigenvalues. So what will be P raised to the power T? So if I do P raised to the power T is, I multiply xd x inverse T times xd x inverse xd x inverse and so on. T times. We have to multiply the matrix with itself P times. Now what is beautiful is, here there is a lot of cancellation, right? So this x inverse cancels this x. This x inverse cancels this x. And so on. And all the x inverse x cancellation happens. So we are left with something beautifully simple, which is x and then d raised to the power of t, because d will get multiplied by itself, right? All the x inverse x gets cancelled, and then x inverse. Okay, so d raised to the power t, what is that? Okay, so rather than write it as d1, d2, dn, let me write it as lambda 1, because I know they will be the eigenvalues. Let me use that notation. So d is lambda 1, lambda 2, dot, 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 lambda n. Okay, where lambda k are eigenvalues of P. They can be repeated, in which case they will be repeated as many times as the arithmetic multiplicity. Okay, if you take the roots of the characteristic polynomial, there will be n roots, possibly with repetition, but those are the eigenvalues. So what is this x d to the power t x inverse? It will be x times, what is d to the power t? Lambda 1 raised to the power t, lambda 2 raised to the power t, and so on up to lambda n raised to the power t. X inverse. Okay, so now what happens as t goes to infinity? This tells you that if you could, this is a big suppose. Not all matrices, are diagonalizable, right? All matrices are not diagonalizable. So there is a big suppose here, but we do know that there are nice matrices which are diagonalizable. Whatever I am saying applies to those. Now, what is the good thing about it? Can I take a limit as t goes to infinity? What happens to the number lambda 1 to the power t, lambda 2 to the power t, lambda n to the power t. Okay. So for that, we know if you take a number and raise to a large power, what happens? Well, if you start with if your starting number is more than 1, then it will go to infinity when you raise to higher and higher powers. If it's a number less than 1 in absolute value, then it will go to these. By the way, these lambdas are possibly complex, right? So these are possibly complex. X also can have complex, that's fine, okay. But actually, since the original matrix has, X can be taken to be real because for some simple reason. But complex eigenvalues will occur in complex conjugates, okay. The non-real ones will occur in complex conjugates. But anyway, what happens if I take a number, if Z is in C, what happens to Z raised to the power T, okay. So it goes to 0 if mod Z is less than 1. And it is equal to 1 if Z equal to 1. In other cases, it may not converge. Okay, in other cases, it may not converge. So Z raised to the power T, if mod Z is less than 1, that will go to 0 because it becomes smaller and smaller. Mod Z to the power T will become smaller and smaller and goes to 0. But if you start with Z equal to 1, it will converge. But let's say even other things like minus 1. What happens to minus 1 to the power T? It will alternate between minus 1 and 1, right? Or if you start with I, it alternates between I minus 1, minus I, 1, I minus I. So it will keep moving. So it will not converge. In other cases, it does not actually converge. Actually, Z to the power T does not converge. In fact, it does not converge. Okay. So if we are hoping to take limit, we just have to see what. So this part is very clear, right? So we will. Anyway, I am making many suppositions. So whatever is needed to make things work, we will make all those suppositions. Okay. So we know that for this, if I have to be able to take limits here, it is better that all the lambdas are either 1 or absolute value should be less than 1. Okay. So let me make another supposition. So first of all, before going there, let me make an observation. Let me make a supposition here. Let me suppose lambda 1 equal to 1 and all the others are strictly less than 1 for all j equals 2, 3 up to n. So let me suppose, this is again a big suppose. I will explain what is really the things that we are supposing. Some of it is actually there, but suppose we have this. Let's finish this simplification. Suppose the first one, I will just arrange it such that the first one is 1 and then the rest of it are less than 1 in absolute value. Then what happens to p raised to the power t? It converges to the matrix X 1 and then every other entry is 0, right? All these converge to 0 times X inverse, right? Because if you see, if lambda 1 is 1 and all these are less than 1, as t goes to infinity, these go to 0 and but this will remain at 1. So you will get X times this matrix 1 and every other entry being 0. Okay, everything else is 0 except the 1, 1 entry. So what does that look like? Okay, so what does that look like? What is the I, j entry of this? what is the I comma j entry here? You have to take the ith row of x and jth row of x inverse, but there is only, so the ith, it will be xik if this matrix I call it E. EKL and x inverse L comma J. I have to sum over K comma L. That is what will give me the I comma J entry of this product matrix. But EKL will give me 1. It will be 0 unless K and L are 1. So that is X I1, X inverse 1 comma J. So that's what I get here. So this entry is X I1, X inverse 1 comma J. So P raised to the power t appears to be convergent. Okay, P raised to the power t appears to be converging to a matrix if we make all these suppositions. First, that it is diagonalizable and that 1 is an eigenvalue of multiplicity 1 and all other eigenvalues are strictly less than 1 in absolute value. Okay, is this okay so far? Any questions on this? Okay, if there are no questions, so let me first say what is it that we are really supposing. What are we assuming and what can we show actually? So to write P as XD X inverse, is that an assumption or is that a given? No, it's not a given. So that P equal to not all matrices are diagonalizable. So let's call it 1. I will label that 1 is an assumption. Okay. So this one is actually an assumption. What about 2? Is that an assumption or a given? Well, part of it is an assumption, part of it is given. Okay, so first of all, let us notice one thing. If you take P and multiply it by the vector 1, 1, 1, 1, 1, what do we get? Okay, so when you multiply by 1, 1, 1, 1, 1, what is the first entry that we get? You take P1, 1, I mean, ith entry will be Pi1 into 1 plus Pi2 into 1. So we get the row sums of P. What are the row sums of P? They are 1. Okay, so if it's not clear, let me write here P11, P12 up to P1n. That's the first row, right? When you multiply this vector with all entries 1, 1, 1, dot, 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 1, what do we get in the 1, 1 entry? So in the the 1 entry, the vector, we get a new vector. This entry will be P11 plus P12 plus dot, 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 P1n. That's the row sum of that first row sum. But that is actually 1. By assumption of the transition matrix, the row sums are all 1. So you just get 1. And the same is true for every other row, second row, third row, and so on. So you get this. So what this implies is that 1 is an eigenvalue of P with eigenvector, let me call it script 1. So let's give it a name. This, when I write bold 1 or whatever, that is that constant vector 1, 1, 1, 1, 1. Okay, so when I assume lambda 1 equal to 1, no, that's not an assumption. 1 is actually an eigenvalue and I can take that as lambda 1. That's not a problem. Okay, not only that, so this is A. B, all eigenvalues of P have absolute value less than or equal to 1. Okay, all eigenvalues of P have absolute value less than equal to 1. I will show it in a moment. So then what we see here is that, okay, one eigenvalue is 1 is a given. It's actually not an assumption. Eigenvalue 1 is always an eigenvalue. But the real assumption, and in fact all eigenvalues are less than equal to 1 in absolute value. So really the assumption is that you should not have any other, there should be only one, should be a simple eigenvalue first of all, and all other eigenvalues, nothing should lie on the unit circle in the complex plane but lie strictly inside. That is the real assumption. Okay, but first, before going back to that, let's prove this. All eigenvalues of P are of absolute value less than equal to 1. Why is that? I think you have done more sophisticated things in the other courses, so I'm kind of going slow. So suppose lambda is an eigenvalue. So let's say PV equal to lambda V. Okay, V is not 0. I mean lambda, so V not 0. Okay, so this is an eigenvalue, suppose. Lambda is an eigenvalue. What does that tell? Well, that says that, so if I expand it, so this says that, okay, by the way, let me put it on the side here. So this comes from fact you may know already, that because row sums are 1. And the general fact is, okay, which I am going to prove it. Okay, so let me prove it. Okay, so let me prove it. So let K be such that Vk absolute value is the maximum of all the coordinates. Okay, so there will be some coordinate. V is a non-zero vector. You pick a coordinate which has the maximum absolute value. Let's say that is the kth coordinate. So then look at the equation number k in this. This is a matrix equation, or there are k equations here, right? So lambda times Vk is the PV sub k, right? The kth entry of P times V, which is pk1 V1 plus pk2 V2 plus dot 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 up to pkn Vn. That is what lambda Vk is, right? That is what, when I expand this into coordinates, the kth equation here is lambda Vk is pk1 V1 plus pk2 V2 plus pkn Vn. This is the kth row of P multiplying the vector V. But let's take absolute value. So lambda times mod Vk is, when I put absolute value here, pk1, pk2, pkn are all positive numbers. I mean, could be 0, non-negative numbers. V1 plus mod pk2, sorry, there is no mod pk2, pk2 times mod V2 plus dot 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 up to pkn times mod Vn. But by assumptions, we know that mod V1, mod V2, etc. are less than equal to mod Vk, right? This is each of these, mod Vj is less than equal to mod Vk, because k is the index for which the absolute value is maximum. So if I bound each of these by mod Vk, then I'll get pk1 into mod Vk plus pk2 into mod Vk plus dot 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 plus pkn into mod Vk. But now pk1 up to pkn is just 1. So this is just mod Vk. Mod Vk, if I take out, the sum pk1 up to pkn is the row sum, which is 1. So this tells me that, sorry, I should have put absolute value on lambda when I took absolute value. Lambda could be a complex number. So this mod lambda is less than or equal to 1 because I can cancel mod vk. Mod vk is not 0. Yeah. And so mod lambda is less than equal to 1. So every eigenvalue is less than or equal to 1 is the fact. Okay, this comes from, you may have seen this more general fact that when the row sums, you take any matrix, you take the row sums of the, not sum of the absolute values in each row. That gives you a bound for all the eigenvalues. So this is a special case of that where the matrix has positive entries. So all eigenvalues have, so really speaking, so what this is saying is assumption 2 is, so what is really assumption 2 here? Two is the extra assumption that 1 is a simple eigenvalue. That means 1 is always an eigenvalue, but it should be a simple eigenvalue. It should not have more than one multiplicity, and all other eigenvalues are of absolute value strictly less than so in the complex plane there is the unit disk and there is the number 1. So there should be one eigenvalue here and the other eigenvalue should be strictly inside. That's the idea. Okay, so all other eigenvalues should be strictly inside. That is what we are assuming. So if P is diagonalizable and 1 is a simple eigenvalue and other eigenvalues are less than 1, then we do get this. Not only that, any questions about these two things? So I discussed the assumptions here a little bit. Now let me go back to the conclusion of what it says. Okay, so going back to the conclusion, so under 1 and 2, under assumptions 1 and 2, we have seen that p to the power of t ij entry converges to x, what was it I wrote? X I comma 1, x inverse 1 comma j, x I1 and x inverse 1 comma j as t goes to infinity for all I comma j in S. But I want to make one more small observation, which is that what is this X matrix? What is the relationship of X to this P? If I write P as XD X inverse, what are these X? What is its relationship to P?
Eigenvectors meant.
These are columns of X are the eigenvectors of P, right? So the columns of X are eigenvectors of P. So note that columns of X are eigenvectors of P. In particular, if you look at the first column, x11 up to xn1, it is the eigenvector for which eigenvalue? For lambda 1, which is 1. And what is the eigenvector for 1? The constant vector, which is 1, 1, 1, 1, 1. Right? So this should be, you can take it to be a multiple of it, but we can take it to be this vector 1, 1, 1, 1, 1. right? Because it's the eigenvector E vector for eigenvalue 1. So then this becomes equal to just x inverse 1 comma j. Because xi1 is 1, then this becomes x inverse 1j. So the big conclusion is under 1 and 2 implies that the entries converge to x inverse. So let's give it the name pi j. Note that it does not depend on I. The key point is because of this first eigenvector being the constant vector, this xi1 is constant. It doesn't depend on I. So we got this another thing that we had noticed in those examples where I showed on Mathematica that so this happens for all I and j in S. This is as t goes to infinity. So we have actually answered our question under some extra assumptions, but still it is a remarkable conclusion that if P is a diagonalizable matrix and we assume that 1 is an eigenvalue which is simple, 1 is always an eigenvalue if we assume it is simple and all other eigenvalues have absolute values strictly less than 1, then the ij entry of P to the t converges to pi j. It doesn't depend on, the limit does not depend on I. So in particular, this was the probability. This P to the Tij, you go back and see what is P to the Tij is the probability that if you start at state I, you will be at j after t steps. So that probability actually converges and to a number that doesn't depend on the starting point. So this is a very good conclusion that we wanted. Okay, so this is what we wanted and we have this conclusion here. Okay, so this solves the question of asymptotic behavior under some special property, under some special assumptions 1 and 2. I now want to relax those assumptions a little bit, but before that, are there any questions? It's also 5:20. I can also stop and do that next time. Or first anyway, let me take questions if there are any about this.
So this transition matrix have always one is a eigenvalue and this is simple by Perron-Frobenius theorem, we can say.
Okay, so I will come to that. So you already jumped to the thing. I was coming to it slowly. But yes, so 1 is an eigenvalue we already showed. That it is a simple eigenvalue. Yes, so if you already saw the Perron-Frobenius theorem, Rajesh was doing it in his course. I guess he has already covered it. So one can use, so that is to justify these assumptions. Under what conditions can I say this? So Perron-Frobenius will solve this problem for me to, even without assuming diagonalizability and other things, we can solve. Okay, yeah, I will come to that, but I want to just explain it in a little more detail. First, let me state how I can get the conclusion and then say how Perron-Frobenius helps. Any other questions? If not, let me just go one more step here and complete this. So can we relax? The assumptions. Okay, so not all matrices are diagonalizable. Is there anything like this for all matrices? So diagonalizability is not okay, but every matrix can we reduce it to some reasonably simple form? So is that a familiar thing? So first matrices need not be diagonalizable, but what can we reduce it to?
Triangularizable.
Triangularizable.
Upper triangle matrix we can.
So yeah, that is true. But what upper triangular matrix?
Real symmetric.
You are talking about LU decomposition or something like that.
Any
Want a
complex matrix
conjugation.
can.
I want a conjugation. I want to take a conjugation of P and reduce it to a simple form. What is the simplest form to which all n square matrices can be reduced?
Possibly real symmetric. Yeah, or mission.
If we assume real symmetric, then they can be diagonalized, in fact, by an orthogonal matrix. That's assuming more. It's a very important special case of diagonalizable matrices. Real symmetric matrices are diagonalizable with an orthogonal matrix as a diagonalizing thing, right? The eigenvectors will be orthogonal. I am asking now, I'll come to the symmetric case. That's an important thing. But I am asking going more general. Not all matrices are conjugate to diagonal matrices. But in linear algebra class,
Normal matrices.
no. Normal matrices are slightly larger than symmetric, but they are also diagonalizable. The thing is about normal matrices are the largest class of diagonalizable matrices by orthogonal diagonalization. Let's say here these are diagonalizable by any invertible matrix. So this is a larger class already than this contains symmetric and normal matrices already. Something more general. What can we do with all matrices? All matrices.
Singular value decomposition.
Huh?
Singular value decomposition.
Okay, singular value decomposition is true. Every matrix can be done, but really singular value decomposition is eigenvalue decomposition of AA transpose, really. So it goes back to symmetric matrices, and for me that is not useful. I want the original matrix to be conjugate to a simple matrix. Okay, any other things you have seen? So there is something called the Jordan canonical form. Is this something familiar to everyone or not? I don't know. Is this
Yes, sir.
is familiar?
Yes,
Okay.
sir.
So every matrix is conjugate is to a Jordan canonical form. Okay. So maybe I only have 4 minutes. I'll just tell you what is the Jordan canonical form is. Basically, there are Jordan blocks. So Jordan canonical form means it's a block diagonal matrix. So where the blocks look like this. Okay, so the blocks, okay, so let's say blocks will be, so each block of the form, so there will be some number which is an eigenvalue on the diagonal. The block will have 0 here and 1 on the immediate above, and everything else will be 0. Okay. This is a Jordan block, and this what we get here is a blocks like that. So there will be, so the full matrix can be conjugated and brought to this form. So there will be a Jordan block like this, then another Jordan block of possibly different sizes. Okay, the Jordan blocks can have different sizes, but lambda 1 may be same as lambda 2 and so on. So you can also have 1 by 1 Jordan block, which is just a diagonal entry. Maybe lambda n will be like this. So like this. So there are these Jordan blocks, and every matrix can be brought to this form of the Jordan canonical form. Now that is just as good. For our purpose, we will next time, now I'm run out of time, so I'll not do it, but we will see that instead of having a diagonal matrix, if we have this Jordan canonical form, that would be just as good for us. Okay, and we will be able to push our theorem forward. but let me keep it for lecture 3. I will stop here now. I'll take it up from here tomorrow. Okay. Any questions, comments? I see some of you answered in the chat, but unfortunately I don't see it when I'm lecturing. Yeah. Okay. So if there are no questions, I'll.
There are one question.
Yes, please.
So suppose if we done all this calculation, then what can we conclude from final answer?
So the final answer is that's the key thing. The final answer, as I got here, the conclusion. This is the important conclusion, that after all this, the point is that under some conditions, we are saying that p to the power t I comma j has this limit which does not depend on I. What it means in terms of Markov chain, forget the assumptions. The conclusion is p to the t ij converges to pi j for all I and j. The resulting limit doesn't depend on I, only depends on j. What it means is that if because of this relation between the Markov chain probabilities and the matrix power, what it means is that irrespective of where you start, if you take a very long time and see after a long time, you ask what's the probability to be in state j, that is going to be approximately this number pi j. It doesn't matter where you start. Okay, so this number pi j will tell you the probabilities with which you will be in various states. Now, another question is how to calculate this pi j. That comes from the eigenvector matrix as we saw here. We will see a better description later. Pi j is given by, how do I calculate these numbers pi j? You calculate the eigenvector matrix and inverse and the first column, first row, that will give me. But we will find later that pi is a very important quantity. So the conclusion is that wherever you start, but this is not without assumptions, with some assumptions, wherever you start, the probability that you will be in different states will stabilize to these probabilities pi j. That's what it is. That's the conclusion.
Yeah, good. Thank you.
Yeah. Okay, so then let me stop sharing.